Hi everyone, it's Mr. Baker here, and today we're going to be looking at moments. So today we're going to be answering this question: what was Archimedes on about? What do you mean, who's Archimedes? Archimedes is probably the most famous Greek mathematician and inventors in ancient Greece. He was around about 2,250 years ago, and he said, one of the things he said was, "Give me a lever long enough and a fulcrum on which to place it, and I shall move the world." So today we're going to be finding out what Archimedes was on about. Okay, so have a look at all of these tools here. We've got 3 different tools. What do you think they've all got in common? So we've got a crowbar, and we've got someone using a crowbar here. We've got a screwdriver, somebody screwing something into it. It looks like a computer or something there. And then we've got a spanner here. So what have these 3 tools all got in common? Well, they're all turning. They can turn things, and that's really what we're looking at when we're looking at moments. Moments is all to do with turning forces. So this is our definition of what a moment is. A moment is a turning force, and you can see here I've got some of the key words that you need to be able to use when describing moments. So an effort is when we're pushing down, when we're causing something to move, we would push with a certain effort. The load is the thing that would be on the end of something that we're trying to move, and then we'd be trying to move it around about this point here, and this point here would be called either a fulcrum, or you might have heard of a pivot. So if I've got something heavy that's pulling down on this end here, then I can push down on this side. So I would be lifting my load here by pushing down with an effort here, and I'd be turning it around this fulcrum or around this pivot. Okay, so I've got an example here. This is from the website FET again. Nice little simulation of like a seesaw or something. We're only going to do really quick. I'll show you really quickly something to do with moments here. So here is my pivot or my fulcrum. This is the point about which this thing will rotate about. If I put something on here, then you can see it turns around this point here, and it turns around this point here because there's a force. You can see the force, the arrow here that's pulling down, and you can see that it's a distance from the pivot or the fulcrum. So depending on where I put the weight will depend on how much of a moment I'm getting. And so the further away I am from the pivot or the fulcrum, the larger the moment, the larger the turning force. The closer I am to the pivot or the fulcrum, the smaller the turning force. And I can show that if I put this on here. So if I put something on the other side, you can see, let's just randomly put it there. So I want to lift this thing up. At the moment, the effort that I'm putting on this end isn't large enough to lift the load on this side. So I'd have to increase the moment on this side by moving the object. And now the moment on this side is larger than the moment on this side. So the turning effect on this side is larger than the turning effect on this side. So the effort that I'm putting in is the moment that I'm putting in this side is larger than the moment on that side. Okay, so this is how we calculate a turning force, a moment. A moment equals the force times the distance. Force is in newtons, distance is in meters, and so our unit for a moment is Newton meters. And here's a nice little diagram that shows what it is. So if I've got a spanner and I am pulling the spanner down, what I'm really doing is I'm going to be turning that spanner around the pivot, aren't I there? And the force is going to be the force that I'm pushing with or pulling with on the end of the spanner, and the distance, now it's quite important to know that the distance is going to be the perpendicular distance. So the distance from the pivot to the end of the spanner is going to be this distance here, but the distance we're always interested in when we're looking at moments is the perpendicular distance. You can see the force is being pushed straight downwards, and that's not going to change. However I move this around, the actual force I'm looking at is going to be this force that's going at right angles to this distance here. So this perpendicular distance is the one I'm interested in. So let's say my spanner here is 50 centimeters and I'm pushing down with a force of 80 newtons, then that's fine. Up here I could work that out, but what I need to do is I need to work out the perpendicular distance here and multiply that by the force to find out what the moment is. And I'll show you what I mean with a few examples. Okay, so here we've got a hammer and it's pulling out a nail that they've accidentally knocked into the wrong place or something there. The force that's going to be exerted on the hammer is 50 newtons, and the distance from the pivot is 0.3 meters. So the moment equals the force times the distance equals 50 times 0.3, and it's 15 Newton meters. Top tips: check that the force is in newtons and the distance is in meters before calculating the moment, and the distance to use is the one that is perpendicular to the force. Now if it wasn't newtons or wasn't meters, now it's got to be newtons really, but if it wasn't meters and it was centimeters, then that would be fine. So if my distance wasn't 0.3 meters but 30 centimeters, then I would have 50 times 30, and so I would have 150 Newton centimeters. So if my distance was in centimeters, then I'd have 30 centimeters there instead of 0.3 meters, wouldn't I? And so I would have 1,500 Newton centimeters, and that would be fine as an answer. I just have to make sure that I've got the right unit that I'm using. Either if I'm using centimeters, then I've got to make sure that I write that in the units. Okay, here's another example. Now this one will show you the difference between the perpendicular bit. So this diagram shows a spanner being used to undo a tight nut. The nut was tightened using a moment of 120 Newton meters. Calculate the force needed to undo the nut. Show clearly how you've worked out the answer. So we've got to use the equation moment equals force times distance, and then you've got to rearrange that equation to start off with. So the force equals the moment divided by the distance. Now we've said that it's 120 Newton meters, so the moment equals 120, and the distance that we're using is the distance that's perpendicular to the force. Okay, so this distance here, look, is parallel to the force, so we're not using that one. This distance is just the distance from the end of the spanner to the nut, and it's this distance here that is at right angles to this force, and so it's this distance we need to use. Okay, and we've changed that from centimeters into meters, and that's fine. You can do that. Like I say, as long as all the units are the same, then it's fine. It doesn't really make any difference what you're doing. But in this case, we need to change it into meters so that we can get the units into newtons, because that's what we want, because we've got 120 Newton meters. So we'd have to change the distance into meters so that we'd get our workings out correct. So in this case then the force equals the moment divided by the distance, 120 divided by 0.4, and so our answer would be 300 newtons. Okay, so these are the things then that we've done today. I think these are the things that you should be able to do. You should be able to give the factors that affect the size of a moment, and you should be able to use and rearrange the equation for moments. So what was Archimedes on about? Give me a lever long enough and a fulcrum on which to place it, and I shall move the world. If he can create a turning force large enough, because he's got a large enough distance, I mean, there's no way that he can lift up the world, is there? He's not that strong. Nobody would be that strong. They couldn't put a big enough force in. But if you had a force multiplier, something that you can use to lift it up because of the distance from the fulcrum, from the pivot, then the moment would be increased, and so you would be able to lift it up because your force times your distance, the effort that you'd put in times the distance, would be able to then lift up the world because the moment that you've created would be large enough. Okay, so that's the end of this one on moments. I've been Mr. Baker, and I'll see you next time.